In the previous section, we've talked about length and distances between vectors. Now we want to define some more geometric properties of them. And we also would like to group this definition, for example, of length, distance, and more, in one single mathematical operation. To do so, let's remind to us what we have defined in the previous course, the linear algebra course. We defined the linear map as a function that maps vectors to another vector space and follow two conditions, the additivity and the homogeneity. Remind that additivity refers to some operation to the addition condition to the vector spaces, while homogeneity refers to the scalar multiplication property of vector spaces. We can with the linear map definition in mind, we can define the bilinear map, which is omega, a generic function that takes as argument two vectors in V and outputs a vector in W, in the W vector space. The conditions are the same, which define the linearity, and are again additivity and homogeneity. But now, these two conditions must lie on the first argument and on the second one. That's why we have two equations, and for each equation we express additivity and homogeneity properties together. With the definition of bilinear mapping in mind, we can refer to a special bilinear map that goes from V times V to R, the real numbers. In this case, omega could have some properties. For example, it could be symmetric or positive definite. If the bilinear map is said to be symmetric, it means that if you compute omega of x, y, this result should be equal to omega of y, x. The bilinear map is said to be positive definite if, excluding the null element of the vector space, the omega xx is greater than 0. And if we take the omega to the null vector, then the result should be 0. These are two properties that bilinear mappings can have. Now we define a particular bilinear map, so it should be linear. This function must be linear, that goes from V times V to R and has the previous properties as condition to this definition. So a bilinear map that is symmetric and positive definite is said to be an inner product on V. If we take a vector space and define an inner product on it, we call it inner product space. When we will talk about inner product spaces, it means that in that vector spaces we will be able to compute the inner product between vectors. In a similar way to linear maps, bilinear maps, in particular inner products, can be written using matrices. For example, in linear maps we defined the transformation matrices. Here we can do the same, but remember that inner products are a particular type of bilinear maps that follow also two other conditions, symmetry and positive definite. So let's take a generic basis B on the vector space V, and let's build with this basis two generic vectors on V through linear combination of the basis. Of course, x and y have some coefficients applied to the basis. Then we can compute the inner product between the two vectors x and y. We express the vectors through their linear combination of the bases and apply the linearity. So the coefficients and the sums go out of the inner product. Then the result would be the sum between of E between 1 and n, the sum of J between 1 and n, the coefficients here, and in the middle we have the inner product between the bases, the basis vector. This can be written using the matrices formulation. In particular, we define this x hat as the vector of the coefficients that from that we will be able to express x through the basis b. Sorry. We do the same for y, and our middle terms here are nothing more than a matrix. So the inner product can be written with this matrix multiplication, where the vectors with the hat on top of them are coefficients vectors. This is the general expression. We can say that it is the transformation matrix of a bilinear map. But we can notice even more property, one more property. In fact, because the inner product is symmetric, it means that this term is equal to this term. These two are the same. So, except for the diagonal, all the elements above the diagonal are equal to the elements behind the diagonal. So here you can see that the two elements are the same. In fact, we are expressing through this matrix the inner product, and we can uniquely define the inner product through this matrix. In fact, we just have to explicit the result of the inner product between the bases to compute the inner product between every vector in the vector spaces. Here we have just to define the inner product between b1, 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 bn, 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 and so on, all of these inner products, and then we are able to compute the inner product everywhere else, because we just need the coefficients of the linear combination, for example, of through b, the basis, that generate the vector x or the vector y. Inner product allows us to define some matrix properties. For example, we can define a matrix that is symmetric and positive definite. Don't worry, we will see more of these properties and define and use it a little bit more in the next course, when we will talk about matrix decomposition. So let's move on and take a look to what happens in an Euclidean vector space. We mentioned in the linear algebra course that the Euclidean vector space is a particular case of R of m times n space with n equal to 1. R of m times n is a vector space, so we defined addition and scalar multiplication operations on top of this space, but talking about matrices, we define some more operations. For example, the multiplication between matrices. Before moving on, remember that the Euclidean vector is also a column vector, a particular case of a matrix. So now, with this in mind, we can say that the multiplication between vectors can be a type of inner product. In particular, we will call it dot product or scalar product. In this slide, we made an hypothesis. We say we would like that multiplication between vectors to be an inner product, and we already give him a name, dot product. Now we have to prove that the dot product is an inner product. So we have to prove the three properties of the inner product: the linearity, which means additivity and homogeneity, the fact that the dot product is symmetric, and is positive definite. Since the inner product is symmetric, we just need to prove the linearity for the first element, because the second one is given for free when we prove the symmetric property. So let's start by the symmetric property, which is the easiest one. So we express the inner product as the sum between 1 to m, so through the coefficients, of the multiplication between the coefficients. Okay. Thanks to the real number properties, we can apply the commutative rule. So the symmetric property is easily demonstrated. To prove the linearity in the first element, we put as first element a linear combination between x and y. Here we express again dot product as the sum of the product of the elements of the two vectors. Fine. And then we can apply the properties of linear or of real numbers. We apply distributivity property. We can express this unique sum as the sum of two terms. Perfect. These two terms are lambda, a dot product / inner product, plus psi inner product again. So we have just proved the linearity in the first element, which holds also the linearity on the second element, thanks to the symmetric property. Finally, we can prove the that the dot product is positive definite because the square of the coefficient is always greater or equal to 0, and this sum is equal to 0 when every component is equal to 0, and the only vector that has all components equal to 0 is the null vector. So we have just proved that the positive definition of the positive definite property, and that the dot product is an inner product. The dot product is a particular type of inner product. In fact, we can define other inner products on the Euclidean vector space. For example, this one. I let you prove the three properties of this definition with this definition of inner product. We define the inner product because this bilinear map can induct the norm and the distance. In fact, we can define the norm as the square root of the inner product. And then we already see in the previous section that the distance is induced by the norm, because it's the difference between the two vectors on which we want to compute the distance. Again, the norm can be expressed as the inner product. Pretty straightforward. For example, if we define the Euclidean vector space as an inner product space with dot product as inner product, like here, we notice that the norm induced by this inner product is the Euclidean norm. In fact, if we take the dot product between x and x, here we obtain the square of the components. Since we have to compute this, the norm is defined as the square root of the dot product here, we get the Euclidean norm. Of course, from Euclidean norm, we can induce the Euclidean distance. So, we have proved that from inner product we can induce norm that induces distances. But why we have defined inner product? Well, because we want to, thanks to this mathematical operation, we want to define even more properties of vectors and vector spaces. For example, angles. But before defining angles, let's take a look to this inequality, the Cauchy-Schwarz inequality. I don't want to prove this relationship, but just let's read it together. So this inequality says that the absolute value of the inner product between the two vectors is less or equal to the product of the norms between the two elements, of course. If x and y are not equal to 0, then, since the norm is positive, definite, these two terms are positive. So, the product of positive numbers is still a positive number. Why it's important to us? Because if this is not equal to 0, we can divide both sides by this product, the product between the norms, and get that the inner product divided by the product of the norms is between -1 and 1. This term can be interpreted as a new function that takes x and y as arguments and outputs this result. Since this kind of function outputs numbers between -1 and 1, we can think that this function could be a trigonometric function, because sine, cosine, and so on take values between -1 and 1. And that's what we do. In fact, we define the cosine of the angle, where the angle is between 0 and pi, as the terms we've seen previously. So it's the inner product between the two vectors divided by the product of the norms. In here, we have expressed the norms through the inner product. So the angle we are defining through the cosine and the inner product the angle of the two vectors x and y. In this way, the angle can be interpreted as the similarity of the orientation between the two vectors. How similar the orientation of the two vectors are. Again, in this picture, you can see that the cosine, taking the angle between 0 and pi, is the cosine is between -1 and 1, as we want it to be. If we take a deeper look to the definition of the angle, we can see that the inner product is a measure of an alignment difference between the two vectors, and the norms, the product of the norms, is meant to normalize the inner product using the vector length. The definition of angle and the cosine of angle in machine learning is used as a measure of similarity. In particular, when we have two non-zero vectors in machine learning, sometimes we want to measure their similarity. One of the function of the or measures that allow us to compare two vectors is the cosine similarity, which is exactly the cosine of omega here. Cosine similarity is often used in text. When we want to compute the difference between sentences. So, what are the vectors here when talking about text? Well, every vector is a sentence. And the vector represents the word frequency count for a sentence. So, if we take the kth vector element of x, for example, of a given sentence, this is the frequency count of the kth vector, the kth word. So we have two vectors that represent the word count for each sentence. Here we measure the similarity, the alignment between the two sentences, and we divide by the length. We are normalizing the similarity, dividing it by the length of the two sentences. The result, talking about text, could be between 0 and 1. And 0 means that there are no common words between the two sentences. If the cosine is equal to 1 instead, the two sentences have the same words, but not necessarily in the same order, of course. The cosine similarity is pretty useful in this sense. That's why it is very useful handling text. With the definition of angle in mind, we can define orthogonality. In fact, if two vectors x and y are orthogonal, if and only if their inner product is equal to 0. This is pretty straightforward, because if the inner product is 0, it means that the cosine of the angle is 0, and this happens only when the omega, the angle, is equal to pi. We can see this on the picture. If the two vectors are orthogonal and they are unit vectors, so their length is equal to 1, then the vectors are said to be orthonormal. So orthonormal vectors are orthogonal vectors with length equal to 1. We can also define and find the orthonormal basis. We say that if we take a basis of a given vector space and these two conditions are verified, then the orthonormal basis the basis is orthonormal. What do these conditions mean? It means that if we take two vectors of the basis, they are orthogonal. And of course, if we take the same vector and we compute the inner product between itself, then the result should be 1. Of course, because the same vector is, of course, one is parallel to the other because it's the same. The orthonormal bases are very useful when we think about how we can define the inner product. We've previously seen that an inner product is uniquely determined by the definition of the matrix A, in which we can find the inner product between bases. But here, okay, we have the symmetry that the symmetry of the matrix between the through the diagonal. Okay, but also that if the basis on which we are computing the matrix A is orthonormal, it means that these terms are equal to 0 and these terms are equal to 1. So we have an identity matrix. The computation of the inner product so becomes very easy, because instead of A we have we can put an identity matrix. The complexity of this computation is to find an orthonormal basis and to express these two vectors using a linear combination of the orthonormal basis. In a 2D plane, we can find several orthonormal bases. For example, the canonical basis is orthonormal. Their length, their norm is equal to 1, and they are orthogonal. But we can find even more orthonormal bases on the 2D plane. For example, these two one. These two are very used and useful in quantum mechanics. With the definition of inner product, we have been able to define lengths, distances, angles, and orthogonality of vectors. Now we want to use this concept, this mathematical operation, and leverage it to do other operations, like, for example, project vectors onto other subspaces.